Hi there, everyone. I'm Daniel, and in today's lesson, we will explore cache memory and mapping techniques. By the end of this lesson, you understand how cache works, the pros and cons of different mapping methods, and how to choose the right one for specific needs. Let's dive in. Introduction to cache memory. Cache is a small high-speed memory unit located near the CPU. Its purpose is to store frequently accessed data, reducing the time needed to fetch it from the slower main memory. Why does this matter? It boosts CPU efficiency by cutting delays. The cache operates in a hierarchy. L1, which is the fastest but smallest. L2, larger but slower. L3, shared, largest but slowest. Cache memory techniques. Cache memory techniques. Cache relies on three pillars, which is the mapping techniques, which is the direct mapping, associative mapping, and then set associative mapping. And then two, replacement policies, and then three, write policies. Think of these as rules for how cache manages data. Let's start with mapping. Memory mapping techniques. Mapping determines where data lives in cache and how it is found. The goal: speed plus efficiency. We will compare direct mapping, which is rigid but fast, associative mapping, flexible but costly, and then set associative mapping, a smart compromise. Each has trade-offs. Let's break them down. Direct mapping. Direct mapping is like assigned parking spots. Each memory block maps to one cache line using modulo map. The formula is cache line is equal to block number percentage followed by the number of cache lines. Example, block 10 is an 8-line cache, which is equal to 10 percentage followed by the number of blocks, which is 8, and this gives us line 2. The pros of these are simple but fast, simple and fast, and then the cons: conflict misses. That is, if two blocks fight for the same line, one gets evicted. The visual shows these memory blocks mapped to fixed cache lines via modulo. Notice block 10 and block 18, both mapped to line 2. This is the conflict miss drawback. The rigid 1:1 mapping creates bottlenecks. Associative mapping. Associative mapping. Associative mapping. Think of this as park anywhere mode. Any block can go in any line, identified by tag bits. The pros of this are zero conflict misses, total flexibility, and then the cons are slower searches. That is, it must check all lines in parallel, and also it requires expensive hardware. Needs comparators for every line, but best for high-end systems where speed isn't the only priority. Associative mapping. The diagram below shows memory blocks on the left can occupy any cache line on the right. The cache must compare tags, that is, tag 1 versus tag 2 to locate data. This flexibility eliminates conflicts but requires complex hardware to search all lines at once. Set associative is more like the Goldilocks solution. Cache is split into sets, that is, groups of lines. Blocks maps to a set but can occupy any line within it. Example, a 4-way 8-set cache means 4 lines per set, 8 total sets. The pros of this: fewer conflict than direct mapping, and then faster than fully associative. The cons: moderate complexity but manageable. See how memory blocks at the top map to sets in the middle, not individual lines. Each set, example, set 0 holds multiple lines ways. Block 10 maps to set 2, but can use any line in set 2. This balances speed and flexibility. A comparison table. Let's summarize the trade-off based on flexibility, speed, hardware cost, and conflict misses. So in the technique of direct mapping, flexibility is low, speed is high, hardware cost is high, and then conflict misses are low. In the technique of associative mapping, flexibility is high, speed is low, hardware cost you require no hardware cost, and then conflict misses are high. Set associative, flexibility is medium, speed is medium, hardware cost is medium, and then conflict misses is moderate. Key insights: direct mapping is for more simple low cost systems, and then associative mapping is for high performance needs, and then set associative is for the best balance. Most modern CPUs use this. To recap, cache is critical for speed, direct mapping is simple but inflexible, associative mapping is flexible but costly, and then set associative strikes the perfect balance. You need to choose based on your budget, performance needs, and design constraints. That's a wrap. Thank you for watching.